All right, so in this unit, we are going to be discussing the idea of solutions and what makes something a solution in general. And of course, when we start a new unit, there's always a little bit of vocabulary that we have to work our way through. So we're going to start with that. And so to do that, though, we need to go back in time and review a couple of things that we've covered a couple of different times in the course of this class. So one of those things that we need to cover is like remembering what makes something ionic versus what is covalent. So if something is ionic, it is made up of a metal and a nonmetal. Remember, your metals are located on the right side, or I'm sorry, on the left side of the periodic table. And your nonmetals are located on the right side of the periodic table. Okay. The other thing that can make something an ionic compound would be if a polyatomic ion is present. And so you didn't have to memorize the polyatomic ions, but you may recall that on your periodic table that you get when you get to take a quiz, the polyatomic ions that we work with are on the back of the periodic table. So you should be aware of that. With a covalent compound, you're dealing with nonmetals. So it's a nonmetal and a nonmetal. And remember, your nonmetals are located on the right side of the periodic table. Okay. And then the other thing is like, what does it mean when something dissolves? So like when I was a little kid, I always thought like, when I thought of something dissolving, which really isn't true because I was a little kid and I was definitely way wrong. Like the Wizard of Oz had two very scary things for me. One, or actually like not scary, like life. It was like stuck in my mind and lives there forever. One of them was I was scared to death of the flying monkeys when I was a little kid. But the thing that also stuck in my mind forever was the I'm melting scene from the Wicked Witch, right? And so like they threw water on her and she was like, I'm melting. And so like when I was a little kid, I thought that was dissolving. And that's not actually true. But what it is dissolving is a substance separates into its smallest units or components. And is surrounded by another substance. So I guess if you were to think about it, like you might have like a famous couple or something, or famous people. I don't know. Like, oh yeah, my man crushes, right? You remember that? It was The Rock. It was Dwayne Johnson, right? It was Dave Grohl from the Foo Fighters, and then it's now Ryan Reynolds. Sorry, like my head is moving really, really slow. So that's that. But like, imagine there's like a bunch of like 40-something year-old men who are like hanging out at the place where 40-year-old men hang out, which is like the hardware store. And these three people come in, right? And so what ends up happening is that when those three people come in, like they get mobbed by like these 40-year-old men who have like the man crush, right? So they came in as a unit and then they get separated into their individual parts and then surrounded by the 40-year-old men. Okay. So like that's an example, I guess, of what it means to actually dissolve. So far, so good. At least that's how I feel about it. So that's just a little bit of a review. And of course, chemistry has to do things like make things a little bit more complicated by simply giving you specific vocabulary terms. And there's two specific vocabulary terms that you really are going to need to focus on for this particular unit. One of those is the solute, which is the substance that separates. No, solute. Not solute, that's different. So the solute is the substance that separates. It's the thing that gets dissolved and is surrounded. And it's usually in a smaller amount. Whereas the solvent is the substance that does the dissolving. It's the thing that does the surrounding. And it's usually in a larger amount. So there's a solute and then there's the solvent. And sometimes chemists or scientists will sometimes refer to something as being the universal solvent. That looks like a V. Try to fix that. And that actually is water. Now, I would like to be clear that the idea of something being the universal solvent, like water, it does not mean that water dissolves everything. Like that's actually not true. If that were true, then assuming that when you took a shower last week, you didn't dissolve because you're here. You know what I mean? I mean, most of us shower at least once a week, right? And then we go from there. Some of us shower more than once a day. I am aware of that. Now, but the thing of it is that even though water doesn't dissolve everything, it dissolves a lot of things. So we're going to talk about what dissolving means and what it actually looks like in a few minutes. But before we do that, we're going to practice the identifying something as a solute versus a solvent. So we have James who's deciding to make the Kool-Aid. And when James is deciding to make the Kool-Aid, we are going to use this scenario here to practice identifying solute and solvent and then try to explain how we knew that. So James is going to make the Kool-Aid. He stirs roughly 15 grams of Kool-Aid powdery goodness into 1 liter of water. 1 liter is approximately the size of this container right here. And 15 grams of Kool-Aid goodness, I don't know, is, well, like in terms of mass, like they say that 1 gram is roughly the mass of a paperclip. So it's like a pile of like 15 paper clips-ish. So like, I guess to think about it like that, I hope that you would identify that the Kool-Aid would be my solute and my solvent would be water. Now, the evidence that we have for that would be there is more water than Kool-Aid, and the Kool-Aid is breaking down or separating into its smallest units and being surrounded by water. So that's one example of identifying whether or not the Kool-Aid or solute versus solvent. In another example, we're giving you an actual picture here. And this one is a little bit easier, I think, to identify. So in the next picture, we're looking at carbon dioxide being and the relationship between carbon dioxide and water based on the picture that you're presented with. And so in this instance, we know that carbon dioxide and water do mix because when you think about it, your bubbly beverages like your LaCroix or your Code Red Mountain Dew, they have the carbon dioxide and the water mixed together. So in this instance here, excuse me, sorry. Looking at this, I see CO2 and I see water. And if I'm going to try to identify the solute versus the solvent, anybody want to venture a guess as to which one is the solute? CO2. Agreed. That would be the CO2, making the solvent the water. Some evidence for that is that CO2 actually is surrounded by water in the picture. There's less CO2 than water, meaning there's more water. Okay. And then the next example here is when we're talking about brass. So brass is an alloy. It's a mixture of, in this case, zinc and copper. And we're trying to identify what is the solute and what is the solvent here. And in this particular instance, we have zinc and we have copper. And I can tell you that by simply looking at this, the zinc will be the solute and the copper will be the solvent. Is there anybody who can tell me how I knew that?
There's more zinc than copper. Oh, wait, no, there's less. Wait.
Yep, just reverse it. You were right.
Yeah.
Yep. So what you had said was there is less zinc than copper. And so that means that the copper will surround the zinc. Which means that the zinc dissolves. Is dissolved. Okay. So that's how that one works. And the big hint here is that we're giving it to you in the ratio of like 34% to 66%. So usually the one that's in smaller amount is going to be the solute, and the one that's in larger amount is going to be the solvent. So then, now that we have sort of practiced identifying solute versus solvent, we're going to talk a little bit about what determines if something will dissolve. And there.
What if it's something like pancake mix or something? Because there's more like of the powder than actual water, and it still dissolves.
So the question is, what if it's like pancake mix or something in terms of salt? Okay, so when you make the pancake mix, you get the pancake mix, you get like a cup of it or 2 cups of it or whatever it is, and then you add like 1 cup of water. What's happening there? Okay, so with flour, I don't. It's my understanding that I don't think that flour technically dissolves; it just becomes moistened. There's a sugar component of it that does dissolve, but not all of it is completely dissolved. So you're making more of a mixture there than something that's actually dissolving. Somebody asked this morning, what would happen if you had like an entire container of Kool-Aid and you put in like Kool-Aid powder and you put in like a couple of drops of water, like what would that be like? And I was like, well, it'll appear as the water gets absorbed, and in reality, there will be some dissolving of the Kool-Aid into the water, but there's a limit to how much can actually be dissolved at that point. So let's see. I don't know who's calling me. Okay, so when we are dissolving things, we have 2 things that we have to check off our list to make sure that they actually dissolve. One is the solute and the solvent need to have the same molecular polarity, and 2, the intermolecular forces of the solute and solvent need to be similar. One thing that I like to refer to is the idea that like dissolves like. What I mean by that is polar substances dissolve in polar substances. And nonpolar substances in nonpolar substances. And this general statement here kind of covers both criteria 1 and criteria 2, but we're going to go over like examples of this in a little bit more detail going forward here. So we're going to use the question of will sugar dissolve in water? And the answer to that question is, yeah, sugar does dissolve in water, at least from your personal experience, but we want to talk about why. So looking at this molecule of sugar down here below, the molecule of sugar down here below is C12H22O11. C12H22O11 does not have any metals in it, so that means it's got to be a covalent compound. And if it is a covalent compound, right, we should probably be able to identify the intermolecular forces of attraction present. So which intermolecular forces are present if it's a covalent compound? What would be one of them? We just took a quiz on it, so I know it's fresh in your memory. What could be one of the intermolecular forces of present in sugar? London dispersion forces. Another guess?
Hydrogen.
Yep. So we have London dispersion forces. We have hydrogen bonding. London dispersion forces simply because it's a covalent compound. hydrogen bonding because there's a lot of O's bonded directly to H's. And if I kind of zoom in here a little bit, I can show you that this would be delta negative and this would be delta positive. And if that's the case, there's a bond there that's delta negative, delta positive. So that means it's dipole, dipole.
How can you tell it's negative and positive?
We usually show you when we do this, like this part. So like it just wasn't there. So I wanted to show you. But if you did see the delta negative, delta positive, you might be able to identify. You would have probably said dipole, dipole. So I was just trying to help you out there.
What if it's not there? That's like one of the answers, though.
We would not do. We would not do that. Okay. And then so that makes this molecule polar. Okay. And then if we were to draw this, it might look something like this. If we were to do a model of matter diagram of this. Right, organized, touching, all those things. So far, so good. So then let's talk about water. Okay. You're looking down at the next section here, and in your notes, you've got water. You've got H2O. It's drawn out for you. There's no metal present, right? And as a result of there being no metal present, you should be able to quickly identify that one of the intermolecular forces of attraction is going to be what now? Nope, not yet.
Hydrogen?
Yep, this one definitely has hydrogen bonding. And there's one other force present here. It's not going to be dipole-dipole this time. LDF, London dispersion forces. The reason why it's not going to be dipole-dipole is because there's no other element than hydrogen and oxygen here. So the hydrogen and oxygen is what create a hydrogen bonded directly to the oxygen is what creates the hydrogen bonding. But there's no other element that's here that creates a polar bond. Does that make sense? Hopefully. So that also makes this a polar molecule. And the way that we've drawn this in the past is going to be the way that we're going to draw it in model of matter diagrams here. It's going to have X's, and they're going to be kind of cattywampus, something like this, like so. Okay? Now, maybe we'll put some over here, maybe something like that. Touching, completely disorganized, stuff like that. So then, what happens? So then we know that sugar is going to dissolve in water because your personal life experience should tell you that, right? So what makes the sugar dissolve in water? So what things have to be present or have to have happened in order for this to occur? Well, let's see. The first thing that has to be true is that the intermolecular forces of attraction between the molecules of sugar need to be overcome. And the intermolecular forces of attraction of water the molecules of water also need to be overcome. And then the sugar and the water need to now form new intermolecular forces of attraction to each other. So let's picture quickly, or not quickly, let's picture for a second what that means. That means that the sugar particles, right, are going to have, some energy has to be added or something has to occur to have those intermolecular forces of attraction between those sugar molecules overcome and they separate, right? So when they separate, what ends up happening is you get something that looks like this. You might have one of these, one of these, one of these, one of these, and paired up with one of these, one of these, one of these, and one of these. And you got like this and this and this and this. Okay. Now, the water, as you may recall, when I drew it before, was, I don't want to say compact, but like it was touching, right? And the particles were touching. And so we now have created space in between the sugar particles. And when the intermolecular forces of attraction of the water are overcome, you're now creating space in between the water molecules. So you have space in between the sugar, space in between the water, and when the sugar and the water come into contact with one another, they now, all that space gets filled up, and it looks something like this. So we're simply just showing that the sugar and the water have mixed together, right? And when the sugar and water have mixed together, there was now new space for each of those particles. And again, the other thing that we need to kind of talk about, is that, again, going back to this, will sugar dissolve in water? The answer to that question is, you betcha. Oh, boy. Okay. And the reasoning for it is that both molecules are polar, and the intermolecular forces of attraction are similar. Now, you may recall, though, that like sugar had dipole-dipole London dispersion forces and hydrogen bonding, and water had hydrogen bonding and London dispersion forces. But in reality, there was enough similarity in the types of intermolecular force of attraction that allows the sugar to dissolve in water. On the next page, when you get there, on the next page, you will see that we're going to talk about the molecule hexane. Okay. So once you've gotten to the molecule hexane, we can talk about what's going on there. Now, molecule hexane, C6H14, no metals present, right? As a result of no metals being present, it's definitely a covalent compound. And I don't see any polar bonds present. And I also don't see any hydrogen bonded to any oxygen, nitrogen, or fluorine. So that tells me that the really only intermolecular forces of attraction that this molecule can really exhibit is London dispersion forces. So that's going to make this a non-polar molecule. You might recall then that water was a polar molecule, which had London dispersion forces and hydrogen bonding. Now, the fact that the polarity of the molecules is different, and the fact that the hexane only has London dispersion forces and no other, should tell you that hexane will probably not dissolve in water. Yes, sir.
Why is it London?
I believe it was based after a human, the human being that articulated what was occurring there.
His name was London?
Last.
No.
Okay.
Last name.
So the answer to the question is no. Hexane will not dissolve in water. Now, our reasoning for this is going to simply be that the polarity of the molecules is different. And we can have the reasoning that the intermolecular forces of attraction are not similar enough. So again, going back to the water and the sugar, like dissolves like, polar and polar. The hexane in the water, like does not, or unlike does not dissolve unlike, so nonpolar and polar. So those are some things to consider. Now, to continue down this line of thinking and or path, we need to kind of identify what makes a covalent compound different than an ionic compound other than metals being present. Okay. So one of the things that we need to talk about is that covalent compounds, you may recall, are held together by bonds. Okay. And what's important about that is that the actual unit, smallest unit, is the molecule. So if I was to draw carbon dioxide, I would draw something like this. And I would have it bonded together as its smallest unit. Okay. Water, as we've drawn multiple times already, we're just going to draw as a bunch of X's here. Okay. And if we draw carbon dioxide into the water, we would draw something that looks like this. That smallest unit stays together and becomes surrounded by water's smallest unit, which in this case would be the molecule of water. And then ionic compounds are held together by attractions. And they're really strong forces of attraction. So ionic compounds are held together by attractions. And you might recall that other parts that make up ionic compounds would be considered ions. Specifically, there are cations, which you might recall to be positive, and anions, which you might recall to be negative. So that means that the smallest unit of an ionic compound is an ion. So if I was to draw iron 3 chloride, I might do something like this. Fe, and then like Cl, 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 and then I might show that there are the valence electrons So it feels like we're going way back in time. But instead of drawing lines like we were a long time ago, we're going to show those really strong forces of attraction. And then I'm going to also show that this iron is a +3 charge. The chloride has a -1 charge, and there's 3 of them, like so. Water, though, this time I'm going to draw like this to help illustrate a point. Again, water is going to be bonded to each other, the oxygen and the hydrogen, and this is going to be delta negative and a delta positive and a delta positive. So when the iron chloride gets dumped into water, what ends up happening is the individual ions separate and get surrounded by the water molecules. So if I said something like Fe with a 3+ charge is going to be a square, and Cl with a -1 charge is going to be a circle, and water is going to be an X, right? What I would really see is I would see that I would have, like, say, a couple of squares, and then I would have an appropriate number of circles, like so. And then I would show that water is surrounding all of the smallest unit, which is the ion. Like that. So the difference between an ionic compound and a covalent compound, when it dissolves, is the covalent compound, the smallest unit is a molecule, and with an ionic compound, the smallest unit are the ions that make up the ratio. So what that tells us is that we have a few examples down below. Now, I can see that because they're in the first example, I have calcium, which is a metal, and I have chlorine, which is a nonmetal. So that means that this is going to be an ionic compound. I can see that nitrogen is a nonmetal and hydrogen is a nonmetal. So that means that this is going to be a covalent compound. And then I also see that sodium is a metal, and PO4 is a polyatomic ion. So that tells me that this is going to be an ionic compound. So when I go to draw these structures down below here, pardon? Poly. So when I go to draw these structures down below, I'm going to have a calcium with a +2 charge, make that a square. I'm going to have a chlorine with a -1 charge. Oops. So a chlorine with a -1 charge, and I'll make that a circle. Now the ratio here is 1 calcium for every 2 chlorines, so I need to draw it as such. So I'm going to draw, like, say, 2 calciums. I'm going to draw, say, oh, I don't like that one there. Something like this. And so now what I'm going to do is I'm going to go back and add water to show that my calcium is surrounded by water. My chlorines are also surrounded by water, and everything is dissolved. In the case of NH3, because it's nonmetal and nonmetal, right, I'm going to have nitrogen and hydrogen, right? And so in this case, I should make that green. Nitrogen and hydrogen. So in this case, right, my nitrogen, I'm going to make, like, I don't know, a circle. And my hydrogen, I'm going to make, like, I don't know, a square. But because this is one unit, right, I'm going to draw it to look something like this. and they're all going to be bonded together. So when I draw this as being my smallest unit, I might do 2 of them. Still bonded together, which is really the important part distinction here. And then we're going to surround it with water. Something like that. And then our last example here, we have sodium, which is a +1, which I'll probably make a square. And our polyatomic ion, which we used to draw as 1 unit, we're still going to draw as 1 unit. So I'm going to make that, I don't know, a triangle. So the ratio here is 3 sodiums for every 1 phosphate. So I'm going to do a couple of phosphates here. And I'm going to do an appropriate amount of sodiums to support that, which in this case would be 6 because it's 3 for each triangle. And then I'm going to show that there's water surrounding all of them. Just like that. Making sure that they are not bonded to one another. And that kind of sums up the differences between drawing ionic and covalent substances dissolved in water. So that's going to wrap up today's lesson.